Here I have a strap, and it's fairly well balanced. Yeah, not all that well balanced, is it? At this point on my finger, in this general area. Okay, now if I add a domino to this side, well, I'm going to have to push down with my thumb at a point that's slightly offset from the position of my finger in order to exert a torque in this direction to counter the torque exerted by the force of gravity on this domino. Now, if I take that off, everything's nicely balanced again. Now, if I put this magnet here, I have to bring my thumb over this way so I can exert a torque in this direction to counter the torque exerted by the gravitational force acting on the magnet. Okay, now, if I put the domino on this end, the magnet on this end, in what directions is that torque going to be if I release it, if I remove the torque exerted between my thumb and my finger? Which one is going to exert the greater torque? Well, that depends on the relative masses of the domino and the magnet and their distances from the axis of rotation. As you can see, if I release it, the system stays in pretty good equilibrium. Now, if I move my finger over a little bit toward the magnet, then the domino is going to have a greater moment arm. It's going to exert a little greater torque. And the magnet is going to have a little less moment arm. Its weight is going to exert a little less torque, so that this torque is going to overcome that torque, and the system is going to tend to rotate in this direction, so that when I release it, it'll have an angular acceleration in this direction, this being the positive direction. Well, let's see how that works. Yep, there it goes. Now, that angular acceleration didn't remain constant. As the system moved downward, the angles here changed, and the moment arm actually changed in a way that we're not going to talk too much about. But we'll just observe that the angular acceleration doesn't really remain constant in this case. But the instantaneous angular acceleration when I released the system was what it was. And now in this problem, we're going to assume we have a 20-gram mass on one end of the strap and a 50-gram mass at some position closer to the axis of rotation, and we're going to ask what is the net torque and what is the acceleration of this system. Now we assume, for the sake of the problem, that the 50-gram mass is 6 centimeters from the axis of rotation and the 20-gram mass 15 centimeters on the other side of the axis. The 50-gram mass will have then a weight of 0.5 newtons. So we're going to have a force of 0.5 newtons at the 6 centimeter position. And the 20-gram mass will have a weight, and it's a little hard to read this 9.8 meter per second squared there, but it's 0.02 kilograms, the equivalent of the 20-gram mass, multiplied by the acceleration of gravity to 0.2 newtons. So we have 0.5 newtons acting down here, 0.2 newtons acting down here. The 0.2 newtons at 15 centimeters from the axis, the 0.5 newtons at 6 centimeters from the axis. And the 15 centimeters is going to be the moment arm on this side, because this is a right angle. We have a right angle between that 15 centimeter displacement and the downward force of gravity. And we've also got a right angle here between the 6 centimeter displacement and the force of gravity. So the torques are going to be negative 6 centimeters times 0.5 newtons, because this is a counterclockwise torque, and a clockwise or positive torque of 15 centimeters multiplied by the 0.2 newtons. That adds up to negative 3 centimeter newtons plus 3 centimeter newtons. Well, that turns out to be 0, doesn't it? Okay, well, now, if we have this configuration, then we have no torque, and that kind of corresponds to the first case you saw when I was holding up the strap with the magnets. There was no net acceleration. The torque, net torque, was 0. Okay, now, let's suppose that we go ahead and apply a torque, net torque of 0.03 meter newtons. Now, just for reference, 3 centimeter newtons would be the same as 0.03 meter newtons, since 3 centimeters is the same as 0.03 meters. So that would be the torque, roughly, of the system you see here. Or, if you prefer, of the system where this is absent and the domino is here. Now, of course, one of the torques would be negative, the other would be positive, but they would have a magnitude about 0.03 meter newtons. So, what's the angular acceleration? Well, now I've calculated the angular acceleration here. The angular acceleration is calculated from the fact that the net torque is moment of inertia times angular acceleration. So that angular acceleration is a net torque divided by moment of inertia. So here's my net torque, 0.03 meter newtons, and here's my moment of inertia, but where in the world did that come from? Well, at this stage, we hadn't calculated it. What I did was, of course, I wrote out this much of the solution, and I went down here and calculated the moment of inertia so I could plug it in here. So let's pretend we don't know this yet, and let's just pretend all this isn't here at this stage. Okay, the moment of inertia of a rod. Now we've seen the moment of inertia of this rod or this strap to be 0.0006 kilogram meters squared, just using the 1/12 mr squared, or ml squared. Okay, so that comes from 1/12 ml squared, and it's the same strap that we've been using, and that might not be completely clear if you're seeing this problem not in sequence with the previous, but if so, you can just understand that this comes from I equals 1/12 ml squared for a rod. The strap we can approximate pretty closely as a rod. Now a rod wouldn't have the width of the strap. The strap is this long and this wide. A rod is ideally just a line with density. It has no width, no thickness. But the width and the thickness don't make much difference, so this equation holds pretty well for the rod. I don't think for the strap. So we approximate the strap as a rod, and I don't think that approximation makes a difference of more than 0.1% or so, 1 part in 1,000 to a few parts in 1,000. So that's fairly accurate. Now, for a 50-gram mass at 6 centimeters, the moment of inertia, and that's this mass at this distance from the fulcrum, the moment of inertia is just mr squared. We assume the mass to be concentrated at or very near the 6 centimeter position. So we do mr squared, 0.05 kilograms times the square of 0.06 meters, and we get 0.00018 kilogram meters squared. Check my arithmetic. I'm not 100% sure I've got all the zeros right, but I think I've got them right. And of course, if I've got my arithmetic wrong, this is going to be wrong, and this is going to be wrong. Won't be far wrong. Okay. Moment of inertia for 20 grams at 15 centimeters, calculated the same way, mr squared. It's going to be 0.02 kilograms and 0.15 meters quantity squared, and that gives you a slightly greater result, 0.00045 kilogram meters squared, so that the total moment of inertia we obtain just by adding up all the moments of inertia. The total moment of inertia is just the sum of the mr squareds for all the particles in the system. So the 1/12 ml squared does that for all the particles in the strap. The mr squared is a good approximation for the 50 grams concentrated close to the 6 meter position, and the 20 grams close to the 15 centimeter position. This is a good approximation. So we get this. We add up all the mr squareds. All the mr squareds in the rod are here. The mr squared for this mass is here. The mr squared for this mass is here. We add them all up. We get 0.00123 kilogram meters squared, which we can now divide into our net torque to get our angular acceleration, 24 radians per second squared. Now, accelerating at that rate for 5 seconds, then what's the result going to be? If we are initially at rest, well, whether we're at rest or not, in 5 seconds, the change in the angular velocity omega is the angular acceleration multiplied by the time interval, and that's going to be 24 radians per second squared times our 5 seconds. This means 24 radians per second. Multiplying that by 5 seconds, we get 5 times 24, or 120 radians per second. So the angular velocity from rest is 120 radians per second. Had we started from some other velocity, of course, we would have ended up with some other angular velocity. The change in angular velocity, however, would have been 120 radians per second. So the final angular velocity would be, in any case, the initial angular velocity plus 120 radians per second.